Okay, so for the benefit of folk that are not here, we've just talked about photodiodes, and then we've talked about that bit there, and then this is a graph showing intensity compared to a leakage current, and David likes to chuckle at leakage current, and they're all looking away from me again because they think it's funny. So leakage current is directly proportional to intensity. Right, now we're on to something new, MOSFETs. Okay, so we need to know the diagram, we need to know, to label the diagram, and we need to know how it turns off and on.
MOSFETs.
Right, okay, MOSFETs is your heading, so you don't need to know what MOSFET stands for, but it tells you beside it. So it stands for metal oxide semiconductor field effect transistor. Now, you do need to remember what laser stands for, you do not need to remember what MOSFET stands for. So for MOSFETs you need to know the circuit diagram and the structure of it. So we'll put two headings, the circuit diagram and the structure. Now it's important, now I'm just going to quickly sketch the two diagrams that are in your notes. So look at your notes and put the circuit diagram, the one on the left, underneath the one that says circuit, and then put the one on the right underneath the one that says structure. Now make sure you label the P parts and the N parts. Now the P-type substrate is the main box, and the two N types are inserted into the P-type. Now I'll do it on the board in case you're unsure at all, and then we'll have a look. Okay, so be able to say what the MOSFET is and how it. Oh, you don't have to draw it, but just have to say, identify it from a diagram. Right, good. Okay, right. So you start off by drawing a box, then you put your two N types on top, and then on top of that you can put down your metal oxide and insulate your drain. So you can put on top of that, you get a little line on top of that, and then you've got actual pad on top of that, and underneath you've got another one. It's all on page 33 of your notes. Okay, now to label the parts, I want you to label them. So you've got to have the right lines coming off. So there's three lines coming out the top. These three lines, these here, correspond to these three lines here. So three lines coming out the top of it correspond to three lines on the right hand side of your circuit diagram. And then you've got this line that joins the two together, this one here. Okay, so we need to be able to label all these parts with the correct words, and we'll just make sure we get this right. So we need to be able to label it with, first of all, the gate. Okay, so the gate is the middle line, so this is called the gate. Then we've got the source, which is the one on the left. And then we've got the drain, which is the one on the right. Substrate. Now the substrate, you've got two different substrates. Or the substrate is the P-type substrate. So this is the P-type substrate. P-type substrate. Then you've got the channel. Now where's the channel in your diagram? There's no channel in your diagram. Implants, you get N-type implants. So this is an N-type here, this is an N-type here. These are N-type implants. So just put arrows to them, please, because you can't do it in. And they are N-type implants. So they are implanted into the P-type substrate. And then finally we've got our oxide layer, which is the bit at the top, which is the insulator. So this top bit here is your oxide. In your notes you've also got metal on the top, which is your metal top and bottom plates. So this is metal and this is metal at the bottom. Okay, now when I draw this from now on, I'm not going to label all the parts. I just need to be aware of what the different parts are. So the N-type implants are N-type semiconductors. They're doped, so they have extra negative charge carriers. The P-type substrate is a P-type semiconductor, so it has extra positive holes. Okay? Right, so that's your structure, that's your circuit diagram. Let's go on and figure out how it turns off and how it turns on. On page 33 it goes through a bit of that, but what we can do is I can just show you briefly how it works. It's quite straightforward once we know how it works. Okay, so we need to know how it turns off and turns on. So let's just go back and look at the structure again, and look at the one in your jotter. If this has a current, even any type of current across it, you've got P-type hitting off of N-type. This is all P-type, these are N-types. So just like your P-N junction, you have a depletion layer set up between the P and the N-type. You have some of the little P-types jumping across. So essentially, you've got a diode here. So at these 2 points, now I don't want you to do this on yours, but at this point here, in fact, not even at that point there, all the way around this N-type and all the way around this N-type is like having a reversed biased diode. It will not allow current to flow. Okay? So what they're saying is that you put negative into the source, positive into the drain. So you put negative in here, positive in here, so you don't have any current being able to flow from the negative side across the gap. So you basically have two reverse bias diodes there. So it won't flow. Nothing will flow. So that's the first paragraph there on page 33. Then it says, when a large enough, over 2 volts, positive voltage applied to the gate. So we're saying it needs to operate over 2 volts. A transistor, this is a form of transistor, a standard transistor will work anywhere between 0.5 and 0.7 volts, because that's the voltage that destroys the depletion layer. But on a MOSFET, it's got to be 2 volts to do that. Positive volt applied to the gate, the electric field created between the gate and the bottom plate draws electrons to the gate. This forms a narrow channel of N-type semiconductor just below the gate. This N channel connects the source to drain, allowing current to flow. And I'll draw you that. It's quite easy once you see what happens. And then once it draws all these negative charges up, it allows the current to flow along those negative charges. So if I take that diagram and just explain how it works this way, I only need to draw one of them. So if I draw one, but I won't draw all the different labels on it. All I'll draw is a couple of things. So there's a P-type substrate, you've got 2 N-type implants, and then you've got a plate in the top and a plate in the bottom. Obviously I need to put in my different gates there. So what we're doing is, this is an N-type, this is an N-type, and this is all P-type. Okay, so that's your MOSFET. It's a simple diagram of the MOSFET. Now when we connect it up, the negative goes on the source on the left hand side. So there's negative coming in here, and this is positive coming out here. Now what we need to do is we need to decide to turn it on, and to do that we have to supply a 2 volt supply to the gate. So if we supply 2 volts to this here, so on your diagram there in the sheets, it's got plus voltage at the gate. So plus voltage is at the gate. So this is the gate. If I put a plus volts of around about 2 volts at the gate here, then this becomes positive, this is negative, and because this is positive, it draws up any negative charge it can find. So any negative charge inside the P-type, remember the P-type is neutral, it's not positively charged, it is neutral, so it does have negative parts to it. So any negatives inside this get drawn up. So they all get drawn up towards the top here. So any negatives get drawn up towards the positive. So we end up getting a little line of negatives that are just right next to the positive there. That little line of negatives is enough to allow current to flow from the negative side across the gap and then back up the positive side. So it just runs through this gap here. So because all the negatives get drawn up, it allows a little channel to allow current to flow, and that turns on the MOSFET. Okay, so the positive bit at the top draws negative charge up and allows the MOSFET to conduct across the middle. Now, where you might have this is in place of something like a standard transistor, where you've got like a voltage divider going into it, and then you've got to turn the MOSFET on. It's exactly the same. It's quite handy to understand where the how this would work. In fact, before we do that, can you draw that down? And I'm just going to put these steps on the top. So first thing that happens is we've got a positive, so 2 volts applied to the gate.
Should we have a wee heading on that now?
No, just underneath it. Applied to the gate. So plus 2 volts applied to the gate. The second thing happens is that negative charge gets drawn up through a narrow line of negative charge forms.
You've got your option here.
It doesn't matter.
Does it not?
No, not just for the diagram here. This is just to let you see what happens. So a narrow line of negative charge forms at the top, and then current flows through this. Current flows through this between the N types. Okay, so that negative charge all gets drawn up to the top, and then the current can flow along that little thin strip of negative charge at the top and give us a current. Okay, so that's MOSFET's done. What we need to go into now is basically a lot to do with atomic structure. The first thing we're doing is looking at page 35, and it's called the Rutherford model of the atom. Now, Rutherford was the guy that designed. Has anyone heard about Rutherford before? Done it in chemistry? Rutherford? Okay, Rutherford basically came up with the idea of how the atom is structured, how the proton and neutron in the centre, and how the electron forms on the outside, or rotates around the outside. But the distance between the proton and the neutron, the proton and the electron, the nucleus and the electrons, is so huge that led him to believe that atoms are mostly made of empty space. Okay, so atoms are essentially made of empty space. So how did he do that? So what you need to be able to do is describe how Rutherford showed that the nucleus has a relatively small diameter compared to that of the atom, and most of the mass of the atom is concentrated in the nucleus. Right, so how he did that? Well, he took a source of alpha radiation. Now, can you remember what alpha radiation is? Helium nucleus, which is made up of
4.
So what's that?
Don't know.
2 protons?
2 protons.
2 protons, 2 neutrons. Right, so let's take the head. Rutherford model. Rutherford model of the atom. Now, there's lots of history behind this. Lots of other people came up with different models of how they think the atom looked, but this is the one that stuck. This is the one that makes sense. So how he started off, he took an alpha source. So an alpha source of radiation. Now remember, an alpha source is 2 protons and 2 neutrons. So it fires out a positive piece of charge. 2 protons is a positively charged particle, and it fires it out the way. So he fired all that towards a gold leaf. Okay, a very thin gold leaf. Now the reason he used gold is because they can get it very thin and it stays very strong. So he used a gold leaf here. So he fired this alpha particles toward the gold leaf. Now just to remember, an alpha particle is positively charged. So it's a positively charged, quite large particle getting firing towards the gold leaf. And then he looked at where the particles went. The leaf was so thin that he pretty much assumed that there was only one atom of gold leaf, one atom of gold in the gold leaf. And what he found was that most of the atoms, most of the alpha particles went straight through. Okay? Now, if the alpha particles are positively charged and they go straight through, that tends to mean that the atom is mostly made up of free space. So when he did this, he found that most of them went straight through. However, some of them went through large angles, and that was pretty much it. So what he found was that most of the alpha particles went straight through. Some of them get bent, so some of them would get bent out a bit and go at funny angles, and some of them, very few of them, would actually get bounced back the way. So most came straight through like this. Some of them get bent through at funny angles. Now it could be any angle, and very few actually came back the way. So there was 3 different ways. Okay, so I'm going to name that 1. That's going to be, these are going to be 2 and 2, and that's going to be 3. So when he fired these alpha particles towards the gold leaf, 3 things happen. First of all, most of them went through the middle. Some of them get deflected at funny angles, and a very, very small amount of them get bounced straight back again, or bounce back off things. So this was most, some did that, and a few of them even did that. Okay, so put the copy of that down. So first of all, the fact that the number one is most of them came straight through. This one here, most of them came straight through, which means that an atom is mostly free space. It doesn't hit off anything. If that alpha particle hits off something, it's going to get deflected, it's going to bend, it's going to bounce off it, might even bounce back. But the fact that most of them just went straight through meant that most of the atom hasn't have anything in it. So number 1 tells us that most of the atom is made up of free space. So number 1, most of the alpha particles went straight through. Or particles pass straight through. And this tells us the first thing. The first thing we need to remember is that the nucleus is a relatively small diameter compared to that of the atom. So this tells us that the nucleus has a relatively small diameter compared to the atom. Now, what that means also is that it's mostly free space. Mostly free space. And there's a really interesting, did I ask if anyone was watching that Wonders of the Universe this weekend?
You did, we were.
Well, the one that was on last Sunday was talking about how neutron stars were made. And neutron stars have the same mass as normal stars, but they are extremely small, or tiny compared to it. And he explained that by saying how, since the atom is mostly free space, imagine you took all the atoms and you squashed them down, get rid of all that free space, you would have this extremely dense, extremely small little package that you've got. You could take the whole of the Earth and squish it down. I think he said something about the size of a sugar cube, something similar like that. You could take the whole Earth and squish it down to the size of a sugar cube. That's just ridiculous. Think of how much free space there is in the Earth. All atoms have so much free space, they could just squish it all down, get rid of it all. It's massive.
I did not say like he held up a stone like that size, and then he said that like that if that was a nucleus.
Like there was a mountain.
Electrons would be like
But a bit,
100 miles away.
like, no, but it wasn't quite as far. I think it was about 5 miles away or something like that. If that was a nucleus, was a size of stone, then like 5 miles away would be the electrons. That's just how huge the space is.
So neutron stars actually are that squished.
Neutron stars. Neutron stars are actually that squished. So they've taken a huge star like the sun and squished it right down, get rid of all the free space, and so they have huge amounts of gravity because they're so small, they're so massive, but they're so dense.
They were so powerful.
Yeah. Okay, so the nucleus is a relatively small diameter compared to that of the atom. Right, and the second thing, number 2, so if we go back and have a look, number 2, what we're getting here is that the alpha particles coming firing along here, and then they're hitting off something and bouncing that way, and some of them are even bouncing straight back. Okay, now what number 2 tells us is that if it's going to deflect it like that, that means they have quite a large mass. It means the nucleus is quite a large mass. What's wrong with that?
It's just the way that's in your head.
Thanks, Dave. So, number 2, some of them get deflected at large angles, which means that the nucleus has a large mass. Okay, so number 2, some alpha particles get deflected at large angles. Now what this tells us is that the mass, most of the mass of the atom is concentrated in the nucleus. Okay, because if it was bouncing off these little rotating electrons, then it wouldn't. Most of it wouldn't get deflected these angles straight through. If electrons are going around outside, then they could be going anywhere.
Did they know that before they knew this, did they know there was a nucleus and electrons?
I think they knew a little bit. They knew there was electrons in the nucleus, but didn't know what the spacing was.
And they didn't know how big. Did they know how big they were?
No.
No. Okay.
Okay, so some alpha particles get deflected at large angles. This means that most of the mass of the atom is concentrated in the nucleus. So most of the mass of the atom is concentrated in the nucleus. One more to do, which is the ones bouncing back. So that explains, number 1 explains number 2. What it doesn't really explain is number 3. Why they get bounced straight back. Now, it does say that number 3 suggests that you've got a large positive alpha particle and it's colliding with a large nucleus, which makes it deflect, makes it bounce. But if that large nucleus was negative, then it would be attracted towards that nucleus and it would make it track towards it and then deflect straight through. The fact it's actually coming towards the nucleus and getting bounced straight back the way means it cannot be negative. It means it has to be a positive nucleus. Because if the nucleus is the biggest thing and you get these alpha particles coming along, if the nucleus was negative, then most of them would get deflected straight through because they get attracted towards the nucleuses. But because it's getting bounced straight back, suggests that whatever the nucleus charge is, it's the same as the positive, which means it's getting repelled by it. So they're coming towards it and getting repelled straight back again. And that explains number 3.
So why did those ones go that way?
Because they're not close enough. They're just getting hit off it. They're kind of deflecting off the sides.
So they're kind of doing a bit of that.
A bit of that, aye.
But if they
Doing
came
a bit of
back, they're doing a bit of that.
A bit of that, aye, yeah, Ross, thanks. If only you could film that. Right, so number 3. Okay, a few of the alpha particles bounce back. What this means is that the nucleus of the atom must be the same charge as the alpha particle. In other words, positive. That means positive. Positive things are good. Right. Positive. Okay. So that's how Rutherford proved the model of the atom, and you might be asked what model of the atom proved that there was free space, and you have to say Rutherford. What model of the atom proved it was positively charged nucleus, and Rutherford. You also might get another one asking you about the Bohr model of the atom. We haven't done the Bohr model of the atom, but that might be a question to confuse you. Give you other options, like multiple choice or something. But Rutherford is the guy that made this up, and he's the one that you need to try and remember. Okay, so all about firing alpha particles at a gold leaf, deflecting, and some going straight, most of them going straight through. Right. So we're still staying in the same theme of sort of alpha particles, radiation, atoms. But now we want to talk about radioactive decay. And there's two different types of radioactive decay. In fact, three different types of radioactive decay. How can an atom decay? What are the three different ways it can decay? You've done this as standard group. What are the three ways in which an atom can decay? In fact, what do we call it when an atom decays, Carson?
Radiation.
Radiation, okay? So it is radiation. So radiation is how an atom decays. So when an atom is getting rid of any of its elements of it, any of its electrons or protons, it is decaying. So radiation is just, or radioactive decay. Okay, so what is radiation? Scott, give me one of the forms of radiation. Can you remember any of them? There's three different types.
Alpha.
Alpha, good. We've talked about alpha already. So you have alpha. It's given the symbol that there, and that's the symbol for alpha. It's a little fish, basically. It's got an A on its side, but draw it like that. So that's the Greek symbol alpha. You sometimes get it in exams, looks like an A with kind of wee extra bits on the side, but it should be written like that if you're writing it. Alpha decay, as Alison already pointed out, is what basically?
Helium.
A helium nucleus. So what we need to do now, I know the guys have not done chemistry, I know you're going to be a bit confused by this, but essentially you have to be able to understand how we write atomic symbols. And I'll just detail what these are in a minute. So an alpha particle, that equals a helium nucleus. So if we want to draw that as a helium nucleus, we'd have He for helium, and we say it has 4 on top and plus 2 on the bottom. Now 4 on top means it has 2 protons and 2 neutrons. The 4 on the top is atomic mass, is that right? Atomic mass in the bottom, and in the bottom is what?
Atomic number.
Atomic number. So atomic mass on top and atomic number underneath. So
numbers are number of protons.
Yeah.
And electrons.
okay.
Protons and then protons and neutrons.
Right, so this number on the bottom is the number of protons, this number on the top is protons and neutrons added together. So this is the total mass. 4 means 2 protons, 2 neutrons, 2 in the bottom means 2 protons. So a helium nucleus, or an alpha particle, is just 2 protons and 2 neutrons. So this would equal 2 protons and 2 neutrons. What the hell am I spelling? Not neutrons anyway.
Jimmy Neutron, that's what it was. I was trying to explain the mark.
Okay, 2 protons and 2 neutrons.
Jimmy Neutron.
Right, what's the other type of radioactive decay we can have then, Adam?
Gamma.
Gamma. Right, I'll put gamma. I want to put another one in before that.
Beta.
Beta. Beta, right? And for anyone ever done German? No. Beta is, the symbol for beta is in German is known as a sharp S. It's a B with a big tail on it, like that. Make sure the top bit is a bit small and the bottom bit. It's hard to do. So I'm going to draw that bit better. That's a bit too big. Just draw a B like that, that's fine. That's beta. Beta with a tail. It's a B with a tail on it. And again is a Greek symbol for beta. Now what is a beta particle? Fraser, can you remember? No, it's smaller than a proton. What's the only thing we know of that's smaller than a proton? If I was to tell you that a TV tube works by firing beta particles at the screen, what does a TV tube you fire towards the screen?
Electrons.
Electrons. So a beta particle is an electron. So to write that one, we draw E for electron because it's not atomic. It's not an atom. It's not a whole atom. It's just an electron. So electron is just given the symbol E. It has 0 mass and it has -1, which means it's -1 charge. And all that means is 1 electron. Right. Adam said gamma. Gamma is drawn like that there. Gamma. Sometimes that little hole at the bottom there's a lot tighter in, but just draw it like that, that's fine. David! For goodness sake.
Sometimes they got a kind of Y as well.
Aye, but it is kind of, let's see, sometimes it's drawn as a kind of, I don't know, but the best way to draw it's just like that. That's a gamma. Now, gamma radiation is a wave, it's a particle energy. It's actually very similar to a photon, because a photon is on the electromagnetic spectrum. A photon is a packet of energy. So a gamma wave is a packet of energy. So if it's releasing a packet of energy, there's no loss of actual particles from the atom. So although it's decaying, if it's decaying it's getting rid of particles, if it releases gamma there's no actual change to its structure. So you'll find that gamma doesn't often get released on its own. It often gets released with beta or alpha at the same time. So gamma is just energy. So it's just a little packet of energy. So this is a packet of energy. It's no particles. Now I know I've said that a photon is a particle, but the actual gamma is just energy coming off as the atom decays. Right. So let's just run through what I've said about the chemistry side of it. Two numbers you've got, or in a letter. The letters represents the actual element, the chemical symbol. The number at the top represents the atomic mass, which is the number of protons plus the neutrons, and the number at the bottom represents the atomic number, which is the number of protons only. Okay, so let's just recap what that is. So let's take a helium nucleus again. It's a beta particle, and that was 4 and plus 2 in the bottom. Then He equals the chemical symbol. The number 4 equals the atomic mass, which is the protons plus neutrons. And the number plus 2 represents the number of protons, which is called the atomic number, which is the number of protons. And for the atom to be stable, the number of protons equals the number of electrons, but that isn't always the case, because it could be unstable. Right, what you're going to have in the exam very often, and I'll give you some past paper questions to do on it, is a whole load of different chemical symbols. And then you're expected to say, okay, it releases beta radiation and gamma radiation and alpha radiation. And you write down the chemical symbols for those, and you work out what particles are being released. Right. So, you will not be expecting a whole lot about chemistry to do this, but you need to be familiar with what you're looking at to be able to answer a question on this. And I think the best way to do that is to answer a few questions on this. But before we do that, I want to just finish off with the very last bit, and then we can go on a quick break. Two things: fission, fusion, and kinetic energy. Right, we'll do that in a second. Right, do you want to go for a break?
Yeah.
Right, go for a break, we'll do it now. Okay, so the next part is talking about energy released in nuclear reactions. Now, radioactive decay, you have electrons and alpha particles, everything given off. We also have energy given off. So we want to talk about how, or calculate how much energy is given off in these reactions. So we've talked about the different types of radiation, and we've talked about what the different numbers mean. Okay, but what we also need to know is, what are you going to be asked in the exam about this? And what you get asked in the exam has to do with a thing known as binding energy. So just write the heading binding energy. Okay, so binding energy is how much energy is required to keep the atom together. If you have so many electrons and so many protons, then that is the energy that's keeping all that stuff together in an atom. If that atom then reacts and releases some of its electrons, releases some of its protons, it will have to have released some of that binding energy to let the thing go. So that's where the energy gets released. So the energy that holds the electrons and protons, or holds the atom together, is known as the binding energy. Okay, so the energy that holds the atom together is known as the binding energy. Now, this binding energy depends on the masses of the mass of the atom, the masses of the nucleus, the protons and neutrons, etc. Holds everything together. So the binding energy depends on the mass of the atom. Depends on the mass of an atom. Now, when an atom reacts, releases particles, releases electrons or protons, whatever, then some that binding energy has to be given up to release that. So there's where the energy has been released. So if an atom decays, if it releases particles in the form of radiation, releases any type of radiation, then the energy must get released. Some of that binding energy must get released along with it. So when radiation is released, so if you can imagine, you're actually releasing some of the particles from the atom. So you are releasing some of the energy that held those particles in. So when radiation is released, some of the binding energy is released. Now, how we know exactly how much is that we look at the mass. If the mass, the total mass before reaction will always be more than the total mass after the reaction, because it's lost its mass through the binding energy being released. So if binding energy is directly proportional to the mass, then if it loses mass, then it loses binding energy. So when radiation is released, some of the binding energy is released. This can be seen as a loss of mass. So if we work at the total mass before, the total mass after, they will be different, and the difference allows us to calculate how much energy has been released. Now, to get that, we use the world's most famous formula. Thank God you all get a chance to use it now. What's the world's most famous formula?
V
equals F lambda. I think that's the most famous one. What is it then, Ross? E equals MC squared. Okay, so the formula we use, the most famous one of all time, was E, because it's everywhere, equals MC squared. Now, E means the energy, the binding energy. Sean?
Run out of space in the jotter and I'm not getting a new one.
Okay. E equals binding energy. And that's in joules, as always. Equals the mass in kilograms. And make sure you get it in kilograms. Multiplied by the speed of light squared. Don't ask me why it's the speed of light, but it is. Squared. And that's got to be in ms to negative 1. Now that's a constant. Speed of light squared is 3 times 10 to the power 8. You must remember that. Can't forget that. It's always 3 times 10 to the power 8. And if you don't know it, it'll be the front of the data book, or the front of your data sheet. The other masses which will be at the front of your data sheet will be the mass of an electron and the mass of a proton. So if an alpha particle is 2 protons, then you've got the mass of an alpha particle, because you know the 2 protons. Also, you'll be given the mass of an electron, so you can know the mass of a beta particle as well. So you know all these masses. So the masses can help you add up the masses. So the binding energy equals the mass. Now this mass is the mass, could be the mass defect, which means a difference in mass. So to get the mass in a reaction, so in a reaction, we have mass before and mass after. The difference is called the mass defect. Just remember that, the mass defect. If I can just get the spelling right. Defect. So if you use the mass defect and the speed of light, you can get the energy released. Because all you're doing is saying, right, how much energy before, how much energy after. It's almost the same thing. You don't have to work out the total binding energy before, the total binding energy after. You can just work out the mass defect, E equals mc squared for that. Thanks, Adam. So, right, last thing before we do some calculations in that. We have to talk about how atoms react. Okay? So how atoms react. Write down atomic reactions. There are two types of atomic reactions. They are fusion and they are fission. The easy one to think about, in my mind, is fusion. And I always think of a fusion chocolate bar. I don't know if you still get them, do you? You used to get fusion chocolate bars, which was basically chocolate and raisins and nuts all mashed together.
Is that not a picnic?
No, it's not. It was actually like a chocolate bar, but it all anyway, it was called a fusion, right? Now, to me, if you fuse things together, well, that's exactly what you do. You fuse things together. So a fusion reaction is fusing, bringing things together, bringing atoms together. So a fusion reaction is when two atoms, two or more, come together to form one. So that normally involves a bit of energy required. If you imagine the binding energy, you're taking two atoms with less energy, less mass, and wanting to combine them together to produce an atom with more mass. So you have to supply some energy to do that, and it's very difficult to do that. There is a bit of energy released as well, but it's very difficult to fuse things together. So a fusion reaction is when two nuclei combine to form a nucleus of larger mass. So atomic reactions are two types. The first one is fusion. So you fuse things together. This is when two nuclei come together to form. So this one is two nuclei or two nucleuses come together.
Nuclei.
I'm just trying to make sure I don't make a mistake. And my old eyes take a while to focus between the board and my sheet.
Jay's not here today.
Your old eyes.
My old I don't know, it actually gets worse now. I'm focusing that board and it takes a minute or two to me focus on that. I'm getting old. Two nuclei combine to form a nuclei of larger mass. To form a nucleus of larger mass. Now this is not common. We don't use it a lot in the world today. It is very difficult to do a fusion reaction. If scientists discovered how to do a fusion reaction, then you could get unlimited free energy. It would be amazing, but they can't, because you need so much energy to fuse things together that really the amount of energy you're putting in is not worth how much energy it gives out. So we just forget about it for now. If you want to have some ambition, you will develop a new way of creating a fusion reactor. Now, nuclear reactors these days do not use fusion, they use something else known as what, Fraser? Can you remember? Fission. So 2 is fission.
Fishing or fish on?
F-I-S-S-I-O-N. Fission. Okay? The fission is when a large mass splits into two, normally with the release of neutrons. Okay, so large nuclei, large nucleus splits into two of smaller mass releasing energy and normally neutrons. Okay, so fission, large nucleus splitting up into two smaller nuclei, and then using releasing neutrons as well and energy at the same time.
Is that like a nuclear reactor?
That is exactly a nuclear reactor. It's a fission reaction. Now, in a nuclear reactor, this can happen in two ways. You need to know the difference between the two. Okay? Now, hang on a minute. What you need to know is normal nuclear reactions that we have in nuclear power stations do not happen. Remember, we use some words for this. We use the same words for the emission of photons. Remember the words were? Emission of photons can happen two ways.
Photon can
No. Inside a laser, it is stimulated. But also, it can happen spontaneously. Okay, so the same happens with radioactive decay. Same happens with a fusion reaction. It can happen, the fission reaction, sorry, it can happen spontaneously, or it can be induced to happen by called neutron bombardment. So we bombard them with neutrons, it causes them to split. So fission can happen by spontaneously or through neutron bombardment. So fission reactions can happen spontaneously, which means any time on their own. Spell it right. Spontaneously, or be induced by neutron bombardment. Now, neutron bombardment is what happens inside a nuclear reactor. So that's what happens inside a nuclear reactor. That's a nuclear reactor.
No.
Does neutron have an E?
Yeah.
Why does nuclear not have an E?
Because English is stupid.
So that's what happens in a nuclear reactor. Neutron bombardment happens inside a nuclear reactor. Okay. What we're going to do now is we're going to look at two past paper questions, basically working out the energy involved in nuclear reactors and releasing energy. You will need a data book to help you here, and I'll get you them in a minute. But the questions we're going to look at are going to be, just for the benefit of everyone at home, 2007 question 31 and 2009 question 30. So I'll just zoom in. That's 2009 question 30, and then we also have 2007. We're only going to be able to do the top part of this one, so it's 2007 question 31. I'm just going to do them, and then we'll, if we get time, we'll go over them. If not, we'll chat about it. Okay, so looking at this one, question 30, the first line is asking us to give us R and S. Well, to get us R, we have to find the total mass before and total mass after. It cannot disappear. So Adam says 235 plus 1 gives us 236. And then the top line of the reaction, the right hand side, has to give us 236. So you get 139 plus R plus 2 plus 0. Yeah, because it's 2 times neutrons, 2 neutrons.
Oh.
So what's R going to be? Still subtracting.
5.
It's going to be 5?
95.
95. So R is going to be 95. Can everyone see how R is going to be 95?
Yeah.
Fraser, do you see that? Yeah. So R is 95. So then it says determine the number is equal to R, so that's R, and S. Now S is a number telling how many electrons are being released. Now to do that one, we have to look at the reaction itself. So, how are we going to do that one? How are we going to work out the number of electrons? Okay.
Wasn't that just the bottom?
Okay, the bottom line. So the bottom line, so you get 92 protons, and then you've got 57, 42, no neutrons, and then 1 electron. So what is that going to be? 57 plus 42? 99.
So it has to be 7.
Yeah.
It has to be take it back to 92.
Okay, so it has to be 7 to bring you back 92.
Like, because 7 times negative 1 would be negative 7. So you add
Yeah,
the
that
negative
is
7.
it. You do it there.
Yeah. 1 week.
So what we're saying then, we're saying the bottom line is the number of protons. But because we've got an electron,
No, the bottom line is the number of protons and electrons. The top line is the number
Protons
of protons
or
plus
protons or electrons.
Yeah.
Right, so how come we can get 92 on one side?
But you need to make the other side
You need to
equal.
balance it out.
Negative 7.
But then you remember you're doing a subtraction, so what I'm trying to get is why
you're
you're
adding
subtracting.
on. You're adding on.
Adding
And the negative.
Oh,
Right. So they have to balance each other out. Remember the electron is negative. So that has to balance each other out by giving you a negative number. So what's S going to be?
7.
7. Okay? Explain why a nuclear fission reaction releases energy. So why does it explain why it releases energy? Simple answer, 1 mass.
because the large nucleus splits into two smaller, releasing energy and
No, we haven't mentioned one thing. What was the one thing we have to mention? Where does the energy come from? Energy comes from...
bombardment.
No. Where is it? Why is there a release of energy?
Splitting the atom.
Oh. Binding energy.
Yep. And what's happened in the reaction? Too large, too small. You have a loss of what? Mass. You have a loss of mass. And that loss of mass means a loss of binding energy. The loss of binding energy is a release of energy.
So
Okay.
what would be the exact answer?
I have to check the answer scheme exactly, but explain why nuclear fission reaction releases energy. The release of energy comes from the going from a large mass to small mass and being a mass defect. Mass defect releases energy. Now we'll have to check. I'll have to check the answer scheme for this. Just double check. Then it's the third part here that's the most important. It's the bit that we really need to focus on. Is the masses of the particles involved in the reaction are shown in the table. Calculate the energy released in the reaction. If you calculate the mass before, calculate the total mass after. Remember to put the right numbers in, and then do E equals mc squared to get the actual energy released. Okay, I'll have to do that for that one. And then the second question, do that on your own. You can only do part A of the second question, can't do part B yet.
We're not doing 30B either.
There's no 30B.
There is. 30A. No, there should be 30B.
No, there's no B. I'm not putting it off. Right, sorry. Okay, have a go at that then. Get your answer to that, and I'll have a look at the marker scheme. Okay, so the difficult part of this question, first part is determine numbers represented by the letters R and S. Right, the letter R, this letter R here, is here, and that R is going to be represented by the total mass of all the atoms before and all the atoms after. So you add up the 2, 3, 5, so on the left hand side you get 2, 3, 5 plus 1, and that gives us 2, 3, 6. And what we must say is that the second half of the experiment, this part here, must add up to 2, 3, 6. So you've got 1, 3, 9 plus your R plus your 2, because it's 2 neutrons, plus 0 for electrons. They must add up to give us 2, 3, 6. What answer did we get for that?
95.
95. So R equals 95 for that one. Now to do S is slightly different. S is to asking us how many of these electrons. S is a number. So on the left hand side we've got 92. So it's all about balancing all this out. So left hand side you get 92. That means there's 92 protons or electrons. But then when you start adding these up, you get 57 plus 42, which gives you 99. So it's 99 between these two. But we need to balance it out. We need to get it back down to 92. So how many electrons bring it back down? So it's 99 minus the 7. And notice the minus number here. The minus number here means that it's a negative charge. So it's 99 positives minus 7 negatives gives us the 92 that we're looking for. Now that's not clear in the notes, but you're only going to get practice doing that in questions.
You do your 9s for me?
And that's how you draw a 9! I'll just explain that. Right, for parts 2 there, explain why a nuclear fission reaction releases energy. Well, large nucleus is too small nucleus. A nuclei, you're going to have a loss of mass, mass defect. Mass defect gives you binding energy, release of binding energy. Now I'm just going to check the market scheme for that one.
I just said large too small is releases binding energy.
Yeah, what I'll do, I'll just check the market scheme for that, okay?
You add them in.
Right, part three we need to work out the total mass before, total mass after. So before, you've got, guys, total mass before, you've got uranium and 1 neutron. So you're going to add one of these with one of these. Then afterwards, you've got that, whatever that is, so that's there, plus one of them, which is that there, plus 2 of these, so times 2 of those, and then electrons have nothing. So these 2 here must add up, and then these 2 must add up, and the difference is called the mass defect. And then you do E equals mc squared, using your mass defect for that one, and that gives you the total energy released. So look at the marking scheme. Right, for part 2, there's the answer. So total mass of reactants is greater than the total mass of products, or loss of mass. So I've said loss of mass. You get a large nucleus to too small nucleus, so you have a loss of mass. And that loss of mass is converted into energy using E equals mc squared. Or the loss of mass is a loss of binding energy, which is E equals mc squared. That gets you 2 half marks for that, so I was right, thank God.